In this video, we'll be looking at the Friedel-Crafts alkylation reaction. This is another example of an electrophilic aromatic substitution, and so you'll notice some similarities in the mechanism. So looking at the generic reaction, what you'll see happening here is going to be something that's a bit different from our Friedel-Crafts acylation. I know the names there sound pretty similar, and so it's pretty common to get those confused, but it's important that you're able to distinguish the two because there are certain important differences in terms of when you would want to use one versus the other. So just generically looking at this, if we want to look at our benzene, we're reacting with this benzene with some alkyl halide, some RCl, where our R is this alkyl group. And this is going to be done in AlCl₃, which is our catalyst. And much like any of our other EAS reactions, I'm sure you can predict the product is going to look like this. So this is the generic scheme of this Friedel-Crafts alkylation reaction. And so that is alkylation, right? Which is distinct from our acylation that we've seen in the last video. So with this alkylation, as you can see, we're reacting an alkyl halide in AlCl₃. Whereas when we were looking at our acylation, this reaction involved an acid chloride. We had some R group bonded here, but this is an acid chloride in AlCl₃. But if you remember, there is also a second step, which is that quenching with water, right? We had to react this with water as a second step, and this numbering is also very important. And you can see that that is absent when we're looking at our Friedel-Crafts alkylation. If you're a bit unfamiliar with that mechanism or why we're doing this numbering or why water is reacting, I recommend you check out my last video on the acylation reaction mechanism. But without further ado, let's get into the mechanism for alkylation. So if we're starting off with our alkyl chloride, looking something like this, what we'll want to do is react first with our aluminum chloride, right? Our AlCl₃. So if we want to draw out the general structure like this, what we'll see is this chlorine here, which has 3 lone pairs, is going to want to go and attack our aluminum. This is going to result in a structure, if we want to draw it a bit more to the side now, just to make some space, is going to result in a structure where we have our chlorine here now bonded to our aluminum, and this aluminum still has the other 3 chlorines from before. But what's important to keep in mind is now this aluminum is going to have a -1 formal charge, and our chlorine here will have a plus charge. And so in order to sort of satiate this, what you'll notice is the electrons that make up this bond are going to collapse onto our chlorine. This is going to result in the formation of two things, right? We now have this sort of carbocation on our R group, and this is also going to now form our AlCl₄. So we can just write that out, AlCl₄. So these are the two things that we're going to form. And what's important to know with our Friedel-Crafts alkylation is once our chlorine breaks off, this R group is now going to be extremely electrophilic. The presence of this carbocation makes this R group an excellent electrophile, which is also why we'll be using it in this EAS reaction. So now, if we want to take a look at our mechanism here, we can now get rid of this and look at our reaction with the benzene. So, kind of the way that we drew it out for our other EAS reactions, we'll draw out our benzene with its double bonds, and let's explicitly draw the hydrogens here as well. So I feel like at this point, if you have been keeping track of the other reactions, this part should seem pretty intuitive. All we're going to be doing now is reacting our R group here, right, which has its positive charge. We're going to have the electrons in the double bond attack our electrophile here. This is going to give us something that looks like this. Where we now no longer have a double bond here, but we still have our hydrogen. We now have this R group, and we have the original hydrogen along with a positive charge here on this carbon. Now we can have a base come in. Remember, this base could be our AlCl₃ minus. This would work just very well. Or we could use any other generic base. But basically what happens, so what happens now is this base is going to go in, deprotonate, right? And the electrons forming the bond between this carbon and hydrogen are now going to collapse here, reforming our original double bond, giving us a product that looks something like this. We've now reformed or reattained aromaticity, right? Regained aromaticity with the reformation of this double bond. And so we'll have something that looks like this. And again, remember this other hydrogen is still here. And so this is our product for our Friedel-Crafts alkylation reaction. But what's important to keep in mind that isn't very clear with this exact example is the fact that you oftentimes have carbocation rearrangements, right? Or we have rearrangements occurring when it comes to alkylation, which is not something that we've encountered when we were looking at acylations. So to kind of make this clear, let's look at this reaction here. If we want to look at our benzene reacting with, let's say this molecule here, right? And again, this is an AlCl₃. The product that you would often predict would be something that looks like this. We'll have a propyl group, right, attached to our benzene, but that's actually incorrect. What we'll notice happening instead is actually the formation of an isopropyl. So it would look something like this. So let's look at the reason as to why this occurs in this way. So what's going to happen here is if we start off with this 1-chloropropane, right? This one. What happens is when we lose our chlorine, you're going to be forming, at first, a primary let's redraw this. What we'll be forming at first is a primary carbocation. Remember, there's going to be our hydrogen here. But what you'll see is if we undergo a hydride shift, we can actually form a much more stable intermediate, which is this secondary carbocation. So what will happen naturally is upon the dechlorination or the loss of this chlorine here is we're going to undergo this shift forming a secondary carbocation. And so by the time the benzene is actually going to react, it'll actually end up reacting with this secondary carbocation, giving secondary carbocation containing intermediate, which then gives us the isopropyl benzene, as opposed to a propyl. And this sort of rearrangement is something that does not occur in Friedel-Crafts acylation. And so, if you were wanting to create the product that we initially predicted, which would look something like this, you'll notice that won't be possible if we were using Friedel-Crafts alkylation. If we wanted to create this product using something like this, it would not be possible, right? Again, or I guess it makes sense if we just draw it like this, right? If we were trying to go from our benzene here to something like this would not be possible. Instead, if you wanted to form this product, what you would have to do is react your benzene with something like this. Right, this is an H2O. We'd have to undergo acylation. So there are certain cases where acylation would need to be used and alkylation cannot be used, right? If we used alkylation to form this product, we would end up getting something like this, which is not what we want. We don't, and that's because with alkylation, you can undergo rearrangements, whereas with acylation, you do not. And so that's why acylation may be more favorable in some cases than doing alkylation. So that's kind of it. And the main thing here, that was a big difference I wanted to point out between acylation and alkylation, right? With acylation, we don't have our rearrangements occurring, whereas with alkylation, we do. And we also saw why that occurs, right? But we saw the secondary carbocation is obviously far more favorable, far more stable than the primary carbocation. And so, energetically, this is what's going to occur naturally upon the dechlorination of our alkyl halide. And so we can't really help but form this sort of rearranged product, as opposed to when we're looking at acylation. And so, yeah, that's the important distinction to make. And so, based on the product that you're trying to form, it's important that you're able to distinguish and figure out which reaction is going to allow for that product to be formed, whether it's going to be Friedel-Crafts acylation or Friedel-Crafts alkylation. So that brings us to the end of this video. Hoping everything is, making sense. If you have any questions or suggestions for future videos, please leave those down in the comments. And if this video was helpful, please show your support by liking and subscribing, and I'll see you in the next one.